To understand radical reactivity, we must first examine radical stability. The stability of a radical is reflected in the bond dissociation energy, or BDE, of the CH bond cleaved to form it. In general, a lower CH bond BDE corresponds to a more stable radical because less energy is required to generate it. Just like carbocations, alkyl radicals are stabilized by electron-donating alkyl substituents. Primary is less stable than secondary, which is less stable than tertiary. While alkyl groups donate electron density weakly through an inductive effect, this stabilization is primarily driven by hyperconjugation, the overlap between neighboring CH sigma bonding orbitals and the half-filled p orbital, which delocalizes electron density and stabilizes the radical center. Even greater stability is achieved through resonance stabilization. In allylic and benzylic positions, the unpaired electron in the p orbital overlaps directly with adjacent pi systems. Delocalizing the single electron across multiple carbons drastically lowers the overall energy of the radical, making allylic and benzylic CH bonds relatively easy to cleave. Unlike carbocations, radicals generally do not undergo simple 1-2 rearrangements, such as hydride or alkyl shifts. The transition states for these rearrangements are relatively high in energy, so radical intermediates usually retain their original carbon skeleton rather than rearranging to a more stable site. Now, let's look at a crucial concept for predicting reaction outcomes: the reactivity-selectivity principle. When halogenating alkanes, chlorination and bromination exhibit vastly different behaviors. Chlorination is extremely fast, but highly unselective. At 25 degrees Celsius, the relative reaction rate per hydrogen atom for chlorination is 1 to 3.8 to 5 for primary, secondary, and tertiary hydrogens. Bromination, on the other hand, is slower, but remarkably regioselective, showing relative rates of hydrogen abstraction per hydrogen atom of 1 to 82 to 1,600 at 125 degrees Celsius. To see this striking contrast in action, consider the halogenation of 2-methylpropane. In chlorination, even though the primary hydrogens outnumber the tertiary hydrogen 9 to 1, the reaction yields a significant mixture. 63% of the tertiary product, 2-chloro-2-methylpropane, and 37% of the primary product. Because chlorine is so reactive, it cannot effectively discriminate between different types of hydrogens. In sharp contrast, bromination exhibits near-perfect regioselectivity. Reaction at the tertiary position yields 2-bromo-2-methylpropane in greater than 99% yield, leaving the primary product as a mere trace amount. We can explain this striking difference using energy diagrams and the Hammond postulate. Chlorination is strongly exothermic. According to the Hammond postulate, the transition state resembles the starting materials. This is an early transition state. The CH bond is barely broken in the transition state, so minimal radical character develops on carbon. Thus, the relative stability of a primary, secondary, or tertiary radical has little effect on the activation barrier, leading to low selectivity. Bromination, in contrast, is endothermic. Here, the transition state closely resembles the products, a late transition state. The CH bond is substantially broken, meaning significant radical character develops on carbon. As a result, the transition state increasingly reflects the stability of the developing radical, making hydrogen abstraction much faster at more substituted carbon atoms and leading to high selectivity. Beyond reactivity and selectivity, radical reactions also have important stereochemical consequences. Recall that an alkyl radical center adopts a trigonal planar geometry with sp2 hybridization. The unpaired single electron resides in an unhybridized p orbital that extends equally above and below the molecular plane. Because the planar radical center presents two electronically equivalent faces, the incoming reagent has an equal probability of attacking from either the top face or the bottom face. When a planar radical intermediate is formed in an achiral environment and a single new chiral center is created, attack from either face produces a one-to-one mixture of opposite enantiomers, a racemic mixture, resulting in an optically inactive product. Next, let's explore the thermodynamics and regioselectivity of radical addition to alkenes. When a halogen radical adds to an unsymmetrical alkene, it displays distinct 𝑎𝑛𝑡𝑖-Markovnikov regioselectivity. This outcome is governed primarily by the relative stability of the radical intermediate. The bromine radical attaches to the less substituted carbon of the double bond, placing the developing radical on the more substituted carbon and yielding a more stable secondary or tertiary carbon radical intermediate. However, a fascinating question arises. Why does this peroxide-catalyzed radical addition work smoothly with HBr, but fail with HCl or HI? The answer lies in the thermodynamics of the two propagation steps. For a radical chain reaction to sustain itself efficiently, both propagation steps should be thermodynamically favorable, and in the classic HBr addition, both steps are exothermic. First, with HCl, the addition of a chlorine radical to the alkene is exothermic. But the second step, abstracting a hydrogen atom from HCl, is strongly endothermic because the HCl bond is exceptionally strong. In the case of HI, hydrogen abstraction from HY is exothermic because the HI bond is weak. But the first step, addition of an iodine radical to the double bond, is endothermic because the resulting CI bond is too weak to offset the loss of the pi bond. However, HBr represents a unique thermodynamic sweet spot. Both the addition of a bromine radical to the alkene and the subsequent hydrogen abstraction from HBr are exothermic. Because of these thermodynamic constraints, the classic free radical addition of hydrogen halides to alkenes is practically viable only for HBr. Finally, let's briefly look at autoxidation and radical inhibitors. Autoxidation is the slow, radical-mediated oxidation of organic compounds, like ethers and lipids, upon exposure to air. Because molecular oxygen exists in its triplet ground state with two unpaired electrons, it readily reacts with carbon-centered radicals to form alkyl peroxy radicals. These peroxy radicals can then abstract weak allylic or benzylic hydrogens, propagating a radical chain process that converts organic substrates into hazardous hydroperoxides. To prevent this degradation, we use radical inhibitors, or scavengers, such as vitamin E, BHT, or hydroquinone. These inhibitors donate a hydrogen atom to propagating radicals, trapping reactive species directly. For instance, hydroquinone donates a hydrogen atom to a peroxy radical, forming a resonance-stabilized semiquinone intermediate. It can then donate a second hydrogen atom to trap another radical, cleanly converting into stable quinone. Because the resulting inhibitor radicals are heavily stabilized by resonance or steric hindrance, they cannot efficiently sustain the chain, effectively terminating the radical propagation process. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.